All right, so we talked about last time, there's two mean value theorems. There's the mean value theorem for derivatives that we talked about last time, right? And remember what that was with a picture. That just means that if a function is smooth, then between the two endpoints, if the function is smooth, so it's continuous and differentiable, then there has to be at least one place in between the endpoints where the rate of change of the function is equal to its average rate of change, right? Where the derivative equals the slope of the secant line connecting the endpoint. So that's the mean value theorem for derivatives. The mean value theorem for integrals is a little different. So what this says, the best way to think about this is with a picture. So let's take this function. We've got some function f of x on the interval from a to c. And if I'm looking at the area under the curve, so here's how you want to think about this. There's going to be some average value of the function on this interval that's going to be defined this way. If we redistribute the area as a rectangle, so it has a constant value, whatever that constant value of the function is, that's its average value. So imagine that we've got a two-dimensional calculus grinder, and we're just going to grind this function down, and the rubble is going to fall down into this pit. And we're going to grind it down until the rubble fills in any divots and it's exactly level, right? Does that make sense? How do the areas, the purple area under the curve and the orange area underneath the line, how do they compare? They're equal, right? Give me thumbs on that. Everybody get that? Okay, so then all we have to do, if I want to find the average value of the function, which is just the value of that line, right? The y value of that line, I'm just going to divide the area. Purple area and orange areas are the same. I'm just going to divide the area by its width to get the height, right? Everybody see that? So how's this work then? So we know that the area under the function, this complicated looking purple area, from A to B is the same thing as, we're going to call this value right here f of c. That's the average value. Why do we call it f of c? It's kind of a weird thing to do, but usually we're trying to find the place where the function has its average value. And the place where that happens, that x value, we call c. So then the value of the function at that place is its average value. You could call it something else if you wanted to. Instead of calling it f of c, we could just do something like, I don't know, we could just call it whatever you want to call it. But I don't know what else to call it, because that's what we always call it, is f of c. That stands for the average value. So then that height times the width, which is just b minus a, those are equal areas. This one's a rectangle, that one's complicated, but they're equal, right? Everybody see that? So to solve for f of c, all I have to do is just divide each side by b minus a. And that's how we define the average value of a function. Okay? Make sense? Now what this is kind of nice to do, this is useful because like when we're doing like real world physics, and you're trying to find the work that's done on an object, that would be something like this. We looked at an example the other day, right? If we look at a force graph, let's just say that this is, that's force as a function of distance. Okay, like we're going to push, this is distance and this is force. So we're pushing, and as we push through a distance, the force changes a little bit. If I want to find the work that's done from, let's say, A to B, the work that's done is just the area under that curve, right? We could do the same work by pushing at some constant force through that entire displacement from A to B, right? What would that constant force be? It would just be the average value of this complicated changing force. Everybody get that? So I would just redefine something that looks like maybe has about, well, not, it's going to be taller than that, isn't it? It's going to be something like, something like that. That's probably not quite exactly right. But we would just call this f of c, and the work would just be f of c times b minus a, right? Everybody get that? Okay. So let's practice this. It sounds complicated, but it's really not. So what if we wanted to, for example, find the average value of this function on the interval from -2 to 2? Okay. So what is the average value? How would I find that? Okay, good. It's going to be the area divided by, the width of the interval, right? The area divided by its width is going to give you the average height of the area, right? Everybody get that? So f of c is just going to equal the integral. Here, let's just write it out. The integral of 4 minus x squared dx from where? Okay. And what does that represent, what I just wrote there? That's an area, right? When you talk about a definite integral, it represents an area. So that divided by 2 minus -2, right? So what does that give us? What is that integral? Okay, 4x minus x cubed over 3. And now what could we do here to make this a little simpler? What do you notice about that integrand? It's even, right? The integral of an even, a function, integral of an even function over symmetric limits. What's our shortcut? Yeah, we double it and we go from 0, right? And why is that an advantage? Yeah, 0 is so easy to plug in, right? It's easy to evaluate the function at 0. Okay, so then this is going to give us 2 times that integrand, or that antiderivative, sorry, from 0 to 2. Well, what's the value of that at 0? Yeah, see how easy that is? So then we're just going to get, and all that is over 4, right? So then what is that? If I evaluate this whole expression at 2, what am I going to get?
8 minus 8/3.
Yeah, what's 8 minus 8/3? 16/3. Good. Times 2? 32/3, yeah. So we get 32/3 over 4, which is the same as 8/3, right? Okay, so that's the average value of our function. Okay? Make sense? Okay? Now, that's the first part. So this equals average value, or f of c. Okay, the second part is they want to know, where does the function equal its average value, or where does it have its average value? How would we find that? Yeah, just set the function equal to 8/3 and solve. That's not calculus, right? So what do we get here? Our original function is 4 minus x squared. So for part B, we just say 4 minus x squared equals 8/3. So what's that give us? So if I push x squared over to this side and subtract 8/3, what do we get? What's 4 minus 8/3? 4/3. So what's x equal to? Plus or minus? Yeah, what's the square root of 4 is? 2 over the square root of 3. And so if I rationalize that, what do I get? Now we don't have to, but what if we did? 2 square root of 3 over 3. Do we keep both of those? Which one do we keep? Do we keep any of those? 2 times... Oh, actually, you know what am I saying? Oh, hold it. Something's goofy here. Oh, no, that's right. 2 times square root of 3 over 3. Square root of 3 over 3 is less than 2, isn't it? I mean, times 2, right? That's less than 1 times 2. So both of those, there's 2 places where that happens on our domain. Both of those are legitimate. They're both in our domain. Okay? And if we want to just see this, here, let's just look at it. Hey, all right, I had it graphed. Good deal. So there's the function, right? Everybody see that? That's our function from -2 to 2. If we want to add up the area of that thing, well, it's 8/3. Tells us right there, right? Everybody see that? That's the integral where, I mean, a and b are just sliders, so we can pick the value. A is -2, b is 2. F of t, there it is, right? Okay, and it gives us 8/3. If I want to graph the area, I think I can do that somewhere here. I'm assuming. Okay, there it is, right? So there's the redistributed area. How do the areas, the blue area under the arch, how does that compare to the red area under the red rectangular area? They're equal, good. And so then the average value of the function is just that value right there, right? Which is what we say it was, 8/3, right there, okay? Where does it happen? It happens there and there. And those are decimal equivalents of whatever we had, right? 2 radical 3 over 3, positive and negative. Okay? Give me 1 to 5 on that. Is that all making sense? Okay? Okay, there's for your notes. Okay, you guys walk me through this one, please. Find the average value of sine x, 0 to pi. What am I going to do? Okay. So it's the integral of... Good, from 0 to pi over... Okay, so just pi, good. Okay. So then that's equal to 1 over pi times... What's the antiderivative of sine? Negative cosine, right? From 0 to pi, okay? You wouldn't necessarily do this, but what if I wanted to make that a positive cosine instead of a negative cosine? What would that do to the limits of integration? Just flip them. Yeah, I could, if I wanted to, write that as cosine x evaluated from pi to 0, just backwards. Doesn't matter, either way. Okay, so then that gives us 1 over pi times, what's the cosine of pi? -1, so negative cosine of pi is +1 minus negative cosine of 0 is, what's cosine of 0?
So -1.
-1. Okay, what the heck? How come we got, oh, that's right, yep. So I get 2 over pi. Make sense? Okay, that's the average value, right? What's that?
Nothing.
Okay. Does 2 over pi seem reasonable? It does. How come? Okay, but there's one quick, say it again. It would, we don't know yet because we haven't found out where it equals that. But why does that seem like a reasonable average value for a sine function? What if we had gotten like, let's say we got something like 5 over pi. That would have been unreasonable. How come?
Less than pi?
If we had 5 over pi. You could have looked at that right away and realized, we probably screwed up.
Because it goes up to, it's equal, it goes up to 1.
Yeah, okay, right? Because the max value of sine is 1. So the average could obviously never be bigger than 1 for a regular sine function, right? This sine function isn't multiplied by, the amplitude's 1 of this thing, right? So you know it has to be less than 1, which it is. Okay, that makes sense. Okay, do they want us to find, where does the function equal its average value? So what do? Yeah, just set sine x equal to 2 over pi. Now, how in the world are we going to do that? Yeah, honestly, that's how. I mean, like, what would we do to find the numerical value of that? How do you solve for x there? Arc sine. Right. So x equals arc sine of 2 over pi, right? Okay, makes sense? Now, see how well you guys remember this. So where's the principal domain of arc sine? So if you do an arc sine function on your graphing calculator or on any calculator, it's going to give you back an answer in what? It's going to give you back an answer with what restrictions?
That's a good question.
I mean, like there are an infinite number of places where sine x equals 2 over pi because sine goes forever in both directions. So the y value is going to hit that y value literally an infinite number of times. Your calculator doesn't want to give you an infinite number of values. So where is in what quadrant of the unit circle does an arc sine function give you an answer? Quadrant 1, right. It gives you an answer in quadrant 1, but then you have to be smart about that and think, like in our case, we're going from 0 to pi, right? Okay, so 0 to pi is what quadrants? 1 and 2, right? So we'd have to take any answers in quadrant 1 that would also occur in quadrant 2. We'd have to include those also, right? Does that make sense? So where would the sine equal 2 over pi? Well, it would happen in quadrant 2 also, wouldn't it? Everybody get that? Like if I looked on my unit circle, like let's just say that this is the place right here where the y coordinate is 2 over pi, right? Sine, yeah. Because that's what we're asking for, isn't it? Right? Doesn't that make sense? We're asking for the sine of what angle is equal to 2 over pi, right? So we want to know, what's that angle, okay? But if I find that angle, where's the other place that's going to happen between 0 and pi? Where else would the sine have that same positive value? Yeah, it'd be right over there, wouldn't it? Everybody see that? Everybody get that? Remember this stuff from last year? So let's just say that we're going to call this, x, because that's what we're solving for. So if we get back some value from our calculator for x, how am I going to find this other value? Subtract x from pi. Yeah. I'm going to go pi and then subtract backwards x to get to that angle. Right? Everybody see that? Okay. And then we would just do that on our calculators. We would just plug in What's the mistake that if you're not careful, you're going to make? No, that's not the one I'm thinking of. What's the mistake that some of you are going to make carelessly because you're going to forget to do this? What's it going to be? Yeah, you got to be. Look, it's in degrees mode. What do I need to be in? Radians mode. There you go. Okay. Okay, so we would do arc sine. How do I do that here? I probably go. Is that how you do it on here? Okay, yeah, I mean, you probably could have just typed that, honestly. I bet you could. So arc sine of 2 over pi gives you that. There it is. What is that? Who knows? I mean, that's just some angle in radians. So it's rounded 2 places, it's 0.69 radians, right? Okay, so then if that's one solution, what's the other one going to be? Pi minus that. Yeah. Okay. Make sense? So those are my 2 solutions. Good? Give me 1 to 5. Is that all making sense? Okay. We're getting there. So now let's do one exclusively with technology. Because here's where we're kind of getting to a point where now a lot of things we can do, we know enough that we can use technology to answer some interesting questions. So why don't you guys try this? Bust out Desmos and try to do this, please. Use technology to find the average value of this function on that interval. And then I want to know, where does the function on its domain, where does it have those values? So what do we do here? This is so easy. It's just the integral divided by the width of the area. Okay, you guys tell me, how do I do the integral in Desmos? See if you remember. INT from negative pi fourths to pi fourths of what? Well, no, of 2 secant squared x, right? Of f of x. Right? What else do I need? It's not giving me an answer yet. What am I forgetting? So I get 4. Okay, but divided by, now we're going to divide this whole thing by pi fourths minus negative pi fourths. Right? And we get that. Is that what you got? So there it is. That's the average value. Okay, does that make sense? Make sense? Okay, now what would I do? So there's the first part. We answered it. So that's f of c. Okay, how would I answer part 2? Where does the function equal its average value? What would I do? Using technology. I'm not asking you to do the integral. Come on now. What does that mean?
You say x equals.
X equals da 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 da. That's my guess.
Mm-mm.
To find the y value? We already have it.
What's our goal here?
I want to know, where does the function, this is not calculus stuff, where does the function have its average value, which we just calculated? Put it in for x?
We're looking where it equals x, so we want to.
Okay, where the function equals that value, right? Okay, so in other words, what I want to do is I want to graph the function. I'm going to graph f of x. So there's my function. Now I can go ahead and set this thing up so I don't need to have a great big window. What do I want to set my window to go from? Yeah, pi over 4 to negative pi over 4, right? So we're just going to go from negative pi fourths to pi fourths. And we'll go ahead and go in steps of pi fourths. So there it is. Okay, now there's my function. What am I going to do with it? How am I going to find the places where it equals that average value? Okay, so I don't want to call it, I have to call it something different. I could call it like y. Y equals that value, right? Okay. So where are the places? There and there. There they are. Positive or negative 0.482 to 3 places. That's the answer to part B. Okay?
I know. Only 24 more days.
We'll have less than you usually.
Oh.
Poor Jimmy, what's he gonna do?
Jimmy,
with
yeah,
you?
you're gonna be the
Everyone
only
else
one
is-
in here.
Jamie, we're just going to do a ton more calculus.
Oh, he says. You can watch Slope Dude.
There's going to be a bounce
Or the
house now.
quadratic formula.
I was going to say, Sarah, holy cow, you just
For like
dialed
days
me
straight.
in. Is there a big bouncy house or is that one a little bit?
Okay, good?
Bouncy house.
I'm done.
Oh.
No,
okay.
it's a 90